Come on, everyone. Let's start off. The last thing that we did was density. We started with the fluid mechanics. Like I said, when we try to study fluids, right, it is preferable we study density instead of mass. Similarly, instead of force, we prefer to study in terms of pressure. So if you see, actually, it resembles a lot to loss of motion. The only thing, we instead of force, we call it pressure, and instead of mass, we take density. So what is pressure exactly? Pressure, we take the symbol to be P. So when you take a body and immerse in a fluid, so just imagine, you're putting your hand inside of water. Or currently, when you're sitting in your room, you are actually immersed in air. You're surrounded by air molecules. We don't feel it, but it is there. The molecules of the fluid collide with the surface, generating a force along the normal. We'll talk about that. And this force per unit area is called pressure. If you have been in a plane, right, you must have had this thing, the ears are ringing. Had that sensation? Or when the plane is being take off, you can feel it actually, the ears are this thing. Or when you're in a lift or an elevator, sometimes, even when you have an elevator which is going little fast, you can feel it, your ears, something like that, you get a pop kind of thing. You feel like, as if something is bulging out. Or you guys are too small, they won't allow you for skydiving, but once you become big and when you go for skydiving, right, what they do, they take you in a normal aeroplane, okay, with windows open and everything. So in your aeroplane, when you go, actually it is what do you call? There is a compression, right? The whole thing is sealed, and they maintain a pressure of 0.8 times atmosphere pressure inside. They don't maintain a complete P naught inside an aeroplane. That is the reason it actually feels weird in a plane when you're sitting for long, right? First thing, some people have that thing; they can feel the difference, right? And the second thing, your taste buds also get deactivated, so food also really doesn't taste that good. And I think food is also bad, anyways, right? That is one. And yeah, in a plane, things the experience is really not that great. Don't maintain 1 P inside. They maintain the pressure slightly less. And if you ever seen your aeroplane ka door, right? How is the door? The door actually opens by pushing it out. They don't have any proper sealing or anything there for your aeroplane ka door. You're getting it? Meaning when the plane is on the ground, even you, right? You must have seen the air hostess, right? The air hostess, right? The thin lady, right? Without much strength, she herself single-handedly pulls that whole door and closes the thing. If you have observed that, next time observe that. It is pretty easy to open the door. You just need to push and it goes out. There is just some two hydraulics there. You push it and it goes out. The reason is this, because the inside the pressure is zero 0.8 and outside the pressure is P naught. There is a difference of 0.2 P naught and 1 P naught is 10 power 5. You will see that, right? That is almost 2 into 10 power 4. And if you take the area of the door to be like 2 meters square, that comes to around 4 into 10 power 4 or around 4,000 kgs of force, 4 tons. So when the plane is actually cruising, it is almost impossible for a human to go and push the door and open the door, right? But when it comes, pretty close to the ground, the inside and outside the pressure actually gets similar, and then you can push the door and it comes out. So anyway, so why do you get this pressure actually? Or if you ever been in a pool, right? And once you go deep into the pool, like even 4 or 5 meters, did you ever feel like something is just pressing you inside? You will feel that. So there, it is a different story. The pressure is more, your body feels compressed. So when you go for the skydiving, right? I was saying, I went once. So what they do, they put you in a plane and they go like a spiral. They take you 3 kilometers up. So when you're in the plane, you can literally see your body bulging up. Matlab, your gases in your stomach start expanding because the outside pressure is small, right? And you will feel your whole body is little, don't feel that comfortable. It feels little bulged. So when you're living in high altitude, that is one of the problem. You get a lot of gas. And but anyway, it is not for long. They'll take you up. I think it is a 15 minutes car ride, and then they jump from there. Yeah, you don't exactly jump. They tie you in front of them like a kangaroo ka baby, and that person jumps. Right. I think you should do that around 10 or 15 times. And then you should get trained. You should get a certificate that you can jump alone, and then you can jump on your own. Expensive, but yeah, it's a one and a thing experience. And once you jump, right, I think the total free fall is for 30 seconds. After 30 seconds, is going to open the parachute. So for 30 seconds, you're just falling. I think within 10 seconds, you'll hit a speed of around 180 to 200 kilometers per hour. You reach terminal velocity. You stop accelerating, you reach terminal velocity. But the problem is the wind gust speed is around 200 kilometers per hour and it is pretty cold, right? So, and it is directly hitting your face. So they give you some goggles kind of thing, which are tight fit, but the rest of your face can feel that cold. So I and my wife went long back. So when we were getting into the plane, there was a Chinese guy who did that thing and he came down. And that guy was like, beautiful, beautiful, open your mouth, good photo, karke he went. I don't know why he said that. I said, theek hai. My wife thought if you open the mouth, you get good photo. So while jumping now, so they have a GoPro camera on the guy who is jumping. He takes all your photos and videos. My wife opened her mouth. You know, you should do this, huh? When you're going on a bike or a car. Do you ever notice if you just the wind is blowing you at 100 kilometers per hour, right? It really hits you hard. You open your mouth, you can't close it back. Getting it? Your mouth just open, you're like karke. Her entire photos were hopeless. She still regrets it till today. And from that day, she started hating Chinese. This was this was long back, even before Galwan, 2017 or 18, I guess. So there, never open your mouth when the wind speed outside is 200 kilometers per hour. You won't be able to close it. And then they open the chute after 30 seconds, and then you get a big jerk kind of pull, but still you're going fast enough. The whole thing goes off like what? 3 minutes, may 5 minutes, may you'll get down. So the whole experience is like 20 minutes, 15 minutes in a plane, and then 5 minutes drop. You should definitely do that, but you should be 18 plus, and don't do it in India. Definitely don't do it in India. Right? Huh? But if you have a revenge on someone, you want to get them killed, you can plan it out. And that is there, but don't try it here. Anyway, so if you look at this, so if you have a surface, now see the best thing about this, when the molecules collide with the surface, now it doesn't matter what kind of surface you have. So when the molecules collide with the surface at any angle, basically these are all oblique collisions. Tell me one thing, if a molecule collides obliquely, the force will be still in which direction? The force is always along the normal. Remember that? So it doesn't matter how the molecule collides with the surface, it always exerts a force along the normal. That is why pressure always acts perpendicular to the surface. So most people think like this. Why is pressure acting perpendicular to the surface? No, it is wrong. It is reverse. You define the pressure in such a way, the force is along the normal. That way area is pressure. Are you getting it? So when molecules collide with the surface, even though they're colliding obliquely, so all these are oblique elastic collisions. Right? And the force due to pressure is always along the normal. So like I said, but it is the reverse way. You defined the pressure that way. So this is the reason why you get pressure. So once you go high into the atmosphere, the outside the number of molecules are decreasing, so less molecules are colliding with your surface, so you experience less pressure. When you go deep into the water, the number of molecules are more, they're more rapidly hitting you, right? So you experience more pressure on your skin. Now the reason why we don't feel it normally is because there is something called your BP, blood pressure. Your blood molecules also inside, they're hitting the surface from inside. The air from outside is hitting, both balance out, so you don't feel a difference. So you feel right now what you're feeling is normal. You don't feel the atmospheric pressure. But once I put you in a container or room where the pressure is less, you can start feeling it because your blood pressure is more. I don't know whether it ever happened to you. When you go to high altitude areas, right, you start bleeding from the nose. Ever happened? Or you must have seen people. If you go to a high altitude area, this is the reason, when you go to high altitudes, you should not just keep climbing continuously. There is something called acclimatization. You need to give your time, body to get used to it. If you're going to Ladakh anytime, the first 2 days, you just need to shut up and sit in the room for 2 days without doing anything. Right? Because you go in a plane, you will feel it the moment you get out of the plane. The moment you get out of the plane, you'll feel it like, boss, there is something different about this area. The air will feel pretty light. You're breathing, but you're not getting enough oxygen. So your body does adjust. Your body can adjust up to 60% oxygen levels. And I think there the oxygen is around 65-70% of the normal. So once you go there, you have to give your body around 2 days so that you can move around a little. But it takes around 15 to 20 days for your body to get used to that area. This is one of the reasons why it is very difficult to fight wars on mountains. So most people think, tomorrow if there's a war between India and China or India or Pakistan and they're fighting on Himalayas, you just can't send soldiers from here. They go there and just collapse. So what they do, right? Right now we have we have something called mountain regiment, right? We have 2 regiments. So each regiment, right, has 3 battalions. Like there are 3 groups. So what happens? One group is on the top of the mountain. They are the ones who are defending us. There's a second group who is there below the mountain who is getting acclimatized. They're getting ready. And one group is on the normal deployment or vacation or anything. So just to maintain troops at that point, you have to maintain 3 times the soldiers. Meaning if you want 3,000 people to be on the top of the mountain, you need to maintain 9,000 soldiers. It becomes pretty expensive. And you can't deploy them suddenly. There is a war tomorrow. You just can't send them in one day. They'll go there and collapse within 5 hours. So you need to put them in this acclimatization range and they have to wait there for a week and then they go for war. So it's a pretty messed up thing. The mountain warfare is completely different ballgame. And I think Indian Army is one of the world's best in that because we have good mountains. So even US the Rangers and Commandos come to Indian training posts and they get trained here in India for mountain warfare. So anyways, so how do we define this pressure then? So pressure P is simply the F perpendicular by area. Which area? The surface area. Every day in your kitchen, the pressure cooker generates a pressure of almost 3 to 4 atm. That vessel on the top generates that pressure. Did you ever see this thing on top of the pressure cooker? Next time, observe this thing. Huh? You have a vessel. On the side, there is a small patch kind of thing. Ever observed that? Did you ever observe that? That is actually the safety valve that explodes when the pressure inside becomes 5 atm. So that the steam can be released. So when I was in school, 7th or 8th standard, I guess. So I saw the cooker and I felt bad about it. I said, yeah, the steam is escaping. Right? My mom is working so hard to cook the food and this bloody steam is escaping. I need to save it. So what I did, on that steam thing, I kept the glass inverted. On top of it, I kept a big, small container of 2-3 kg of weight dal upar, so that the vessel doesn't come up. I sealed it, literally. Right? And it went on, 20 minutes, half an hour, steam was not coming, I was happy. And then boom, karke, this safety valve which is there, that exploded. The entire cooker was gone. It was bent out of shape. The handle melted a little bit. But it was bad. And I was like shit scared, like what happened? I didn't understand only. My mom came running. She said, "What happened?" I told her, "See, I'm saving the steam, but for some reason this thing exploded." My mom didn't beat me, but she was worried, like, don't do such things next time. If it had been exploded, like that thing could have come and hit your face or something, you would have gone. So don't do such things, right? That valve is designed, normally your whistle can withstand up to 3 atm. After that, the whistle blows off. Every time the pressure exceeds 2.5 atm, the whistle goes up. But if you exceed 5 atm, that safety valve blows off. So don't tinker with that safety valve. If you tinker with that, then you have made a bomb in the house. So, yep. Yeah, that is the pressure there. So we can also write this thing as force is equal to pressure into area vector. Now, see, pressure is a scalar quantity. It does not have a direction, but the force has direction. So pressure is scalar, and the direction of force is the direction of area vector. I'll show you how it looks. Now, so what do you mean by that? So when someone says, at this point the pressure is P. So simply force by area. So what is the direction? So the direction depends on nu. So if this was the area vector dA1, a small area, then the force will be in this direction F1, which is P into dA1. Let me give an analogy. Anyone who comes towards me, I'll push you by 1 meter. See the statement. Anyone who comes towards me, I'll push you by 1 meter. If you're coming towards right, which way will I push you? If I'm standing here, if you come towards right, I'll push you towards right. If you come from the front, I'll push you in the front. If you come from left, I'll push you from the left. You're getting the problem there? So the direction does not depend on me. The direction depends on which way you are coming. So pressure simply tells you I'm going to generate this much force. Which way? You tell me which way the area is. Suppose if the area is this way, dA2, then the force would be this way. If your area is this way, then the force would be this way. So it's perpendicular to that. Hope you remember area is a cross B. It's a vector perpendicular to the plane. So if you take any random body there and if you immerse it in a fluid, the pressure will be perpendicular to the surface. Right? All these are perpendicular lines. So the units of pressure is Pascal. And others do keep your cams on. Clear, Ishman? Ishman, any doubts? Hello, Ishman, are you there? Ishman, are you there? Yeah, respond, Nare, God. What are the units of this thing? The unit is 1 Pascal, which is 1 Newton per meter square. So if you apply a force of 1 Newton on a meter square, it's called 1 Pascal. The atmospheric pressure we use the symbol P naught, which is 1.01 into 10 power 5 pascals. This is pretty huge. That means if you take 1 meter square area, that gives you almost 10 power 5 newtons or 10,000 kgs or 10 tons of weight. So in a vacuum, that thing will experience the weight of this thing. Now there is another way you can give the pressure. It is also given as 76 centimeters of mercury column. I'll tell you what it means. Later on when I teach you barometer, we'll show you that. In chemistry, you must have studied this thing, no? 760 mercury, 76 centimeters of mercury column. So what do you mean by that? So the meaning of that thing is when you take the formula rho mercury, GH, density of mercury is 13,600, G is 9.8, and H is 76 centimeters. When you do this calculation, this thing comes to around 10 power 5 Newton per meter square. So that much pressure can lift a weight of 76 centimeters of mercury. Sometimes, they will say like this. The pressure in a surface is 10 centimeters of mercury column. So the meaning of this thing is rho mercury GH. This is 13,600 into 9.8 into 0.1. That's your pressure. Then you can then even say sometimes like this. The pressure at a point is 3 meters of water column. So this is another way of giving pressure. You give the pressure in terms of length of the liquid column. So here you'll take rho water GH, that will be 10 power 3, 9.8 into H is 3 meters. That's your pressure. Sometimes you'll hear the word called gauge pressure. So when you go to this, this mechanic or something, and when you actually see the pressure now, what they measure is gauge pressure. Ever seen that? That guy brings a device like this. So there is a meter here and there is a thing like this. After putting the air, they keep this and they check it out. Observe kiya kabhi? So this machine, what it measures, right? It doesn't measure the actual pressure. It measures the pressure with respect to atmosphere. We call it gauge pressure. So gauge pressure is simply the actual pressure minus atmosphere pressure. It measures the difference with respect to atmosphere. So example, if someone tells you gauge pressure is 5 atm, the actual pressure is 6. There. So that's a bit about pressure. Like I said, this value is pretty huge. Getting it? We just don't notice it because our blood pressure, manages it out and we think it is. But let me show you how deadly atmosphere pressure can be. Where is this?
And it's part of the year 9 science curriculum. What we're going to do is we're going to.
So you can see there, that's a oil cut drum. So they poured water inside and they're heating it up. So the what is happening? The water is getting heated up. It is producing steam. So when you have steam, because it is getting heated up, the steam is going out. With it, the air is also leaving out, isn't it? So you heat it to very high temperature. The steam starts going out, and then what they do? They seal up the top part and they start cooling it down. Now understand what is happening. Inside, you replace the air with steam, isn't it? So once you seal it on the top and you start cooling it down, what will happen to the steam? It starts becoming condensed. It will condense to water. Once it starts condensing to water, inside the steam is going away and there is no air to occupy that space. So it becomes almost vacuum. The pressure starts dropping inside. Are you getting this? Then let's see what happens.
Heating up a little bit of water in the bottom. As it heats the water up, it comes to spray from liquid.
Then you can see how the steam is gushing out.
All that space.
So all the air is being pushed out because of the steam, and steam is replacing the air inside. There, they're removing the flames. The teacher is putting the cap back. There, he sealed it. They're almost sealed. Little steam is coming, but yeah. So now we have to wait it for cool down, but it might take a long time. So teacher takes water and starts pouring on it. Cools down faster. Now, when you're cooling down, the steam inside starts condensing and starts becoming liquid, and you create a low pressure region inside. See, see that again. Hence the whole thing just compresses. That's a proper steel drum, huh? So that if you're not impressed with that, like, oh, okay, big deal about drum. Let's check something big. This is, remember what is this? Oh, railway oil tanker. Railways, right? They send oil on this thing on that. So they brought a big machine. They're doing the same thing. They're removing all the air from inside. Look at this. There. Can you see how it got compressed? That's what happens. That's how strong the atmosphere is actually pushing you. Your blood pressure is just canceling it out. We don't notice it. There. So next time, have some respect for atmospheric pressure. Great. So that's it. So technically, there's nothing much theory on this. What is pressure? Force perpendicular to the area of cross section or area. Let's say a question on this. So we have a water jet. The water is coming out with speed u. Rho is the density of water. A is the area of cross section. If you remember, we did something like this thing in units and dimensions. Find the force exerted on the wall. And we have a wall here, and the wall itself is moving with speed v. And the coefficient of restitution is e. So the water hits the wall and it doesn't completely bounce off. In the B part, this is an important one. The same question again, you will get it in modern physics. This time the wall is at rest and d is equal to 1. This time the water jet is coming at an angle. It bounces off and goes off. Angle theta. Find the pressure due to the water jet on the wall in both the cases. So in the first case, the water jet is hitting along the normal head-on. Second case, you're hitting at an angle. The Beaker result is quite important. You should definitely remember it. Let's try them both. In the first case, the wall is also moving. The water jet is going and hitting the wall with U. E is the restitution. Find the pressure acting on the wall due to the water jet in both the cases. If you throw a person into space, you don't explode, you freeze to death. Your skin is actually airtight. Think about it. That is the reason when you go into the water, why doesn't water enter through your skin? Because your skin is actually airtight and watertight. So we'll talk about that later on. If someone still thinks they'll explode, you should Google it out. In chemistry, they will teach you about this thing. How did you get 0.5, Rishi? I gave E is the restitution. How to do this kind of questions? Ask yourself. Remember, I keep telling you something like this. If something is going with a constant speed or something goes with a constant acceleration, what do? Go and stand on it. Now, these are the words, those are important. Like, maybe it doesn't belong to that chapter, but the idea is still the same. Srihari, you're getting answers without E in the answer. So you're saying E doesn't matter. That's what I'm saying. It's okay to give wrong answers, but understand when it is a blunder. Why did you take E is equal to 1? Question is E is the restitution. Why did you take that? Do what is given, na? Don't do what you want. You're going to change the advance paper when they give you the paper. You'll write your own questions and write the exam. That would be interesting. Chala, try. Let's see the first one. The wall is going with constant speed. Go and stand on it. Why? It's an inertial frame. There is no pseudo force, nothing. So it makes your life easy actually. So take the observer, make him and stand on the wall. So we are solving the problem with respect to the wall. So if you ask this person what is happening, he will say, okay, the water is coming with the speed of u plus v. Restitution is e. We have seen this in collisions. If you hit a wall with u plus v, you'll bounce back with the speed of e times u plus v. That's your speed. Now consider a small cross section here, dx. Area is a. So dm will be, the mass of this small piece will be density into volume, which is area into thickness. And what is the change in momentum? Change in momentum is P final minus P initial. So in this scenario, it will be dm V final minus V initial. So V final will be E into U plus V minus I cap. That will be the direction. This will be minus and minus of U plus V. That will be dm into E plus 1 into U plus V minus I cap. That's your change in momentum. And we know from Newton's second law, force is nothing but dp by dt. And dm is nothing but how much? Rho a dx by dt into E plus 1 into U plus V minus I cap. But what is dx by dt? What is dx by dt? V plus U. Because what is x? X is the distance between the wall and the water jet. So it's all relative velocity. Because you're doing the problem with respect to the wall, the guy still thinks this is U plus V. So therefore, we get force is equal to rho a U plus V whole square E plus 1. This is the force acting on the wall. And what is pressure? Force by area. That will be rho into U plus V whole square into E plus 1. You can ignore the minus and the sign simply indicates the direction. Check it out. All clear with this? Now, since you're doing in a Volca frame, remember, wall is still an inertial frame. So whatever force it experiences, the force will not change with the frame. You get the same answer. Now, if you make the wall at rest, V will be 0. If you make E is equal to 1, then it will be perfectly reflecting. E is 0, it will stop. So there you get all the cases there. Here to the second one. When the jet is hitting at an angle, E is equal to 1 and the wall is at rest. Any doubts on this page, please ask me. This is what I said. Even though I said fluid mechanics, if you see, we are still doing Newton's laws of motion. The whole chapter will be like this only. You will see a lot of NLM, right? And you will it resembles a lot of laws of motion and work power energy. After rotation is over, every chapter we will feel like, part of mechanics only. There will be like 20-30% new and 60-70% will be repetitive. What about the second part? Find the pressure. Water jet hits the wall at an angle theta. How dp is what? Dp is change in momentum, mass into final velocity minus mass into initial velocity. Right, Vedika? So initially your speed is u plus v I cap. Your final speed is e times u plus v minus I cap. So I just subtracted them. Sure. Which part is confusing?
Yes, sir, I understood.
Wait 1 sec. This thing is on low mute. Haan, bolo na. Which part is confusing?
No, sir, I understood.
Got it, na?
Yeah.
What about the second one, everyone? What if the water jet is hitting at an angle theta? Let's see. So this guy is hitting at an angle and bouncing off. We saw this thing in oblique collision. So only the horizontal component changes. The vertical component is unaffected. So this is going with speed u. Take a small mass dm. So if you go with u, you'll come back with u because the wall is at rest and d is equal to 1. So the change in momentum dp will be 2 times dm u cos theta. Is that clear, everyone? 2 mu cos theta. That's your change in momentum. And what is dm? dm is rho a dx. This is 2 rho a dx u cos theta. This is your change in momentum. Hope that was clear. Only the u cos theta component will reverse. U sin theta will be unaffected. So change in momentum will be 2 mu cos theta. M is dm. So when you differentiate this thing by dt, we get force is equal to dp by dt. 2 rho a dx by dt u cos theta. Till here, great, everyone gets it. 2 rho a u square cos theta. Now, when I say find pressure, this is where the problem comes. People think pressure is force by area. Now ask yourself, which area are you talking about? A is not the area of cross section. See, something interesting happens here when you hit at an angle. When you're hitting the wall at an angle, this is area A, the area of cross section. But when this water jet is extended and hits the wall, observe something what happens. The water jet actually spreads out. It is hitting on a much bigger area. This was area A, but you're hitting that red area, which is longer. If you take this angle to be theta and this angle to be theta, this is hitting an area of A by cos theta. If you actually see the cross section, this is how the picture would look. If you look at the cross section, initially it was a circular cross section. Let's say the radius was r and the radius was r. But when the water jet hits at an angle, one side of the cross section gets extended. It becomes like this. This side will remain r, but this side got extended by r by cos theta. It actually becomes an ellipse. Is that making sense? The water jet, when it is coming this direction, when it hits the wall, it is getting extended in one direction. The other side will still remain r. So the area becomes A by cos theta. So the water jet is not hitting area A anymore. It is hitting a much bigger area. Water jet spreads over a bigger area. So the mistake what people do is they think pressure is forced by area. Area is not the area of cross section. So what is the pressure? Forced by area where the water jet exerts the pressure, which is F by A by cos theta. which is 2 rho u square cos square theta. Most people don't get that cos square theta. So this A by cos theta is the area where the force acts. There, that's an important result. You can remember that. Have a look at this. So most people don't get that cos square theta. Oh, Srihari, please focus on the class, right? Don't do all this nonsense. Just focus on the class, boss. Where do you have this much time to do all this thing? Just focus, listen and understand and learn. You type a right answer, I'll say you typed right, okay? Let's keep it simple. This thing, don't make it like a Hindi serial drama or something. I really don't care so much. Just give the right answer or focus and learn, boss. All clear with this thing? So the main catch in this question is that area part. So pressure is forced by area, but which area are you talking about? It is the area where the water jet is hitting the wall. Is this clear, everyone? Vedika, clear with this? Why did it do 2 dmu cos theta? Because it is hitting at an angle.
Yes, sir.
Clear, na? Others, Trishi, Shreyansh, clear with this? Rudransh, got this? Anvita, Aditi, Advait. Great. Then let's see one more. So then, if you see that's about pressure, like it is more of a force question. Next thing, variation of pressure. So how does pressure vary in a liquid? So consider an imaginary cylinder. Inside the liquid. So let's say we have a container. We have a liquid here. We have a cylinder here. So it's just an imaginary cylinder. It is just your imagination. There is nothing actually there. And consider there is a point A here and there's a point B here. Let this height be HA and let this height be HB and let the pressure outside be P naught, the atmospheric pressure. Right? Now draw the FBD of the cylinder. So if I draw the free body diagram of this cylinder, what are the forces acting on the cylinder? The pressure from the top is pushing you, PA into area. The pressure from the bottom is pushing you, PB into area. And your own weight, mg, is acting. And this imaginary container is at rest, isn't it? The liquid is not moving anywhere. So the forces must be balanced because it is an equilibrium. So you can clearly see the difference in pressure PB minus PA into area must be balancing your mg. PB minus PA into area. And what is mg? Density of the liquid, area of cross section, and the height of the cylinder, which is HB minus HA. Area gets cancelled off and you end up with PB minus PA is equal to rho G HB minus HA. You can clearly see this thing is nothing but dP, the change in pressure, and this rho G, this will be dH. So dP is equal to rho G dH. This is your differential form. So a small change in pressure over a height of dH is given by rho G dH. This is the change in pressure for dH. This is the thing which you have to use when you have to integrate. Right? But if you take the point A is on the surface, if A is on the surface, then pressure at A becomes P naught. and HA becomes equal to 0. Then your formula becomes PB is equal to P naught plus rho GH. There, this is your another standard formula. The pressure at a depth H is given by P naught plus rho GH. But this is valid only when rho and G are constant. If your density or gravity is changing, you can't use this formula. Right? And H is the depth from the surface. So then, that is the formula which you learned in school, isn't it? Pressure at a depth is equal to P naught plus rho GH. Now, similarly here, if I take one more cylinder, horizontal this time, and if I consider one more point C here, any doubts on this page? I'll go ahead if you're clear with this. All clear with this page? This is the derivation actually. If you see, we just did what? Equilibrium problem, isn't it? All we did was NLM, forces and balancing everything here. Now, if you take a horizontal cylinder, the pressure will be PB into area. This will be PC into area, right? And you can clearly see PB must be equal to PC. So from here, we can make a statement. So pressure depends only, pressure varies only in the vertical direction. Right? And remains constant in horizontal direction. Now here, there's an important thing. What is up and what is down? What is up and what is down? We talked about this thing in kinematics, if you remember. How do you know what is up and what is down? Anyone? What if there is no gravity? Then how do you define what is up and what is down? So this is an important thing. This will be useful. Again, in oscillations also, this concept is useful. Multiple places is useful. The direction of net force is taken as down. If you take a system, and if you look at the direction of the net force, if you remember, this thing we did even in the last class, yaad hai? The net force is always in the perpendicular direction. What is net force? It is a force including the pseudo force. So this was the same thing which we did in second page. Direction of net force is vertically downward. Because see, systems really don't understand whether you're accelerating. Think about this. If you have a lift which is going up with G, the person inside will experience a pseudo force which will look like the gravity is acting down. Means you can't tell whether you're actually on the earth or whether you're in a lift. Everything will look identical. You're getting it? So currently, right now, imagine if earth was a flat surface, the flat earth theory, right? And that is what they say, this whole thing is accelerating up with G. So we think there is a gravity G acting downward. Anyway, so kind of fine. So you have to include the pseudo force. Let me show an example. See the example. Let's say we have a container fully filled with liquid. This is a fully filled shell at rest. Now the only force acting here is gravity. So what is down? This vertical line is down. Now if I consider some points here, let's call it 1, 2, 3, 4, 5, 6, 7, and 8. What is horizontal? The line perpendicular to this vertical is a horizontal. This is 2. Right now, if I ask you, arrange the pressures in the ascending order, which point will have the highest pressure? The deepest point will have the highest pressure, P5. Then P6 and P4 are equal because they're in the same horizontal level. Then P3 and P7 are equal because they're on the same level. Then P2 and P8 are equal. And then finally P1. This is the order. Clear with this? So as you go down, the pressure increases. At a horizontal level, the pressure is same. Clear? Same question, but if I change it, the fully filled shell, but this time, let's say it is also accelerating with A is equal to G, and your gravity is also present. And you take the same points, 1, 2, 3, 4, 5, 6, 7, and 8. Now if I ask you, arrange them in the ascending or descending order of pressure. Now see what happens. What's the direction of net force? The pseudo force will be Ma, and your weight will be mg. So this is also mg only. So the direction of net force will be this. This is your F net. How much is that? M into G root 2. So this will be M into G effective. So this whole system will think that gravity became G root 2 and it is acting at an angle of 45 degrees. You're clear? So any person who's standing here, they're going to stand like this in this shell. This is how the world will look like. Now, if you look at the points, so what are horizontals now? This is 1, this is 2, this is 3, 4, 5, 6, 7, and 8. Now, what is horizontal? These are horizontals. You're getting the whole idea of what is up, what is horizontal will change depending on your net force. Now, if I ask you who has the highest pressure, who has the highest pressure? The deepest point. What is the deepest point here? 6. Is that making sense? So P6 will be the greatest. Then P5 and P7 are equal. Then, so as you go up, the pressure decreases. P4 and P8. Then P1 and P3. Then P2. Is that making sense? Did you see the whole answer changed? Here P5 was the highest, here P6 is the highest. So what is up, what is down will depend on the direction of the net force. Any doubts on this? If I give you a different number, G root 3 or something, the angle will change. So accordingly, you have to draw a line and check it out. I kept 45 because it is easy to see. And even if you ask you this question, so P6, what is the highest pressure here? P5 minus P1 will be density of the liquid, gravity G, and the depth is 2r. This is the maximum difference in pressure. Here, what is the maximum difference in pressure? P6 minus P2 will be rho. Gravity became G root 2 and the depth is 2r. Clear with this? So G becomes G root 2. So if you accelerate this container, the entire liquid will start thinking the gravity has rotated by 45 degrees and the magnitude became G root 2. Any doubts on this? All clear with this? Clear, na Devanshi? Pratyasha? Advait? 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 Let's see next one. Let's see a question on this. So that's it. So simple story. How does the pressure change? dP is equal to rho G dH. When to use this? You can use this whenever rho and G are changing. If rho and G are constant, then use P is equal to P naught plus rho GH. What is H exactly? The depth from the surface. When you say depth, that means up and down. So what is down exactly? Down is the direction of net force. So whenever you calculate net force, stand on the container and include the pseudo force. Clear with this? So let's say we have a container, rectangular one, completely filled with liquid. The density is rho. There is a gravity g, and this whole setup is accelerated horizontally with a. This is point A and this is point B. L is the length of the container and h is the height of the container. Find PB minus PA. Find the difference between B and A ka pressure. How do you handle this? No, if you have that is wrong. Samyak, you did a big assumption there. You took a big assumption. Like, what is the guarantee the net force when you took it is in this direction? Net force ऐसा भी हो सकता है ना? Because A and G ka value I don't know, L and H ka value I don't know. There is no guarantee that the net force will pass exactly through A and B. You almost got it. You messed up the sign though, right, Arya? See, this is a. I'll show you this thing in a way. Consider a cylinder like this. Consider a horizontal cylinder. And let's imagine the point C here. So if you just look at this point C here, so this is PC into area. This is PA into area, right? And it is accelerating forward. I'm just doing it in the ground trimmer. So PC into area minus PA into area. Basically, you can argue like this, okay? If it is accelerating horizontally, the system will think there's a gravity acting backward. So when you travel horizontally, when you go from A to C, only A will matter. When you go from C to B, only G will matter. Is equal to mass into acceleration. PC minus PA into area. The mass will be rho, area of cross section into length into acceleration. A will cancel. We get PC will be PC minus PA is equal to rho L acceleration. Now you take a vertical cylinder. Whenever you're confused, FBD is always the savior. Now in this thing, if you see, there's only gravity G, isn't it? This is PC into area, this is mg, and this is PB into area. So here you'll get PB minus PC is equal to rho GH. If you add these two equations, this is 1 and this is 2, PB minus PA will be a rho LA plus rho GH. So when you're traveling horizontally, vertical will not matter. When you're traveling vertically, horizontal won't matter. Are you clear with this? Now, why can't I do the previous way, like I said, G effective and all? If you want to do G effective, the problem is this. This was point A. So if you look at the pseudo force, this will be MA. This was your gravity mg. So the net force would be something of this sort. I don't know the value of A and G. So this is the G effective, which is root over A square plus G square. So this is point B. So what you want to find from here, drop a perpendicular. Let's call this B dash. So you need to find this depth here. So pressure will be PB minus PA will be rho into G effective into that length AB dash. Are you getting this? Because now this is horizontal, isn't it? All these black lines will have same pressure. So B and B dash will have same pressure. You're getting the problem there? There is no guarantee that line will pass through AB. Sure with this. So if you want to do the previous way, this was the headache, right? But this is much faster. Like Aito would do like this. So this is the container filled with liquid. I'll go and stand on the container. I will think this is the acceleration, and I will think this is the thing. So when I'm traveling from A to C, I'm only bothered about A. So this will be rho LA. That is down, isn't it? When you go from C to B, this is down. So this is rho GH. Done. Rho LA plus rho GH. Pressure is scalar. You can add it up. Clear? You have to stand on the container and then you should think that A is backward. Is that making sense, everyone? So that's a much faster way. But if you want to do this, this is the problem. You can do it in this thing I showed you in ground frame. There, I showed you in 3 different ways total. So works out. Sure. So the answer is rho LA plus rho GH. There. Take a break. Come back by 9:40. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes. Sure. Next, see the next one. There. So we have a circular pipe here. So this is a vertical circular pipe. It is filled with two liquids. Others comes on. Row 1 and row 2. So one liquid is filled till here. (90° basically. And the second liquid is filled in this space. Both the liquids don't have same density. So this guy is row 2 and the black liquid is row 1. Right? And that is also 90°. So total 180°. Basically, it is half filled. This horizontal line, this angle is theta. Gravity is present and the liquids are in equilibrium and occupy 1/4 of a circle. Find row 1 by row 2. If both the liquids had same density, then theta would have been 0 and the shape would have been something like this. The black one would have occupied this half and the right one would have been occupied by the red one. The densities are not equal. Is the picture clear, everyone? So we took a circular pipe, we filled it with the two liquids. 1/4 of the liquid was black and 1/4 is red. So they occupy half of the thing. And this is how the shape is looking in equilibrium. Find rho 1 by rho 2. Answer will come in terms of the radius is r, angle is theta. Let's see. Ari, I think you got reverse, right? So you're taking the answer reverse, I guess. Yeah. Let's see what are the catch here. Right, Utsa. Right, Pratyasha. See. Same thing. Since it is an equilibrium, consider 2 points here. Let's consider this, okay? This is A and this is B. So just at the bottom there, let's consider these 2 points here. Now, since these 2 points are in equilibrium, right, the PA must be equal to PB. Why? They're at the same horizontal level. The intersection is at an equilibrium. Now, remember what did I say just now? The pressure depends only on rho GH, where H is the height, meaning it doesn't matter what is the shape of the container, right? You can take an amoeba shaped container like this, right? And if I ask you what is the pressure between this point and the ground A here, it doesn't matter. The pressure is simply P naught plus rho GH. As long as the height is same, you can take any shape of the container, it doesn't matter. Is that fine? And you can prove it also pretty easily. See, start from here, go straight down. Let this height be H1. What is the pressure here? P naught plus rho G H1. Travel horizontally, pressure will not change. Then come straight down. What is the pressure? Rho G H2. So what is the total pressure? Rho G H1 plus H2, which is the total height. Are you clear with this? So it depends only on the vertical height. It doesn't depend what is the shape. So then you're great. So if that is theta, this is 90. So this is 90 minus theta. Now it is just all geometry. Then this height will be how much? R into 1 minus sine theta. Because this is R sine theta and that will be 1 minus sine theta. Similarly, on this side, this is theta. If this is R cos theta, then this is R into 1 minus cos theta. And this height, R cos theta. And this height will be R sine theta. There, perfect. All you want is the heights. So what is the pressure at A? The pressure at A will be, which liquid is this? This is rho 1 ka liquid. So rho 1 G, the height, which is R into 1 minus sine theta. This must be equal to the pressure on the right hand side. What is the pressure here? Rho 2, this liquid. What is the height? Rho 2 G, R sine theta plus R cos theta. Because look at this thing, this entire red liquid is occupying this vertical height. rho 2 g r sine theta plus r cos theta. So it doesn't matter what shape I give you, what matters only the vertical height. Then this part of the liquid is occupied by rho 1 again. So that is rho 1 g r1 minus cos theta. Please check this equation. You're done. That is the main idea there. It doesn't matter what shape I give you, just make it vertical. You take always the vertical heights. G will cancel, R will cancel. We get rho 1, 1 minus sine theta. Bring this rho 1 this side. You get cos theta minus sine theta. And this will be rho 2 cos theta plus sine theta. The rho 1 by rho 2 divided by cos theta, that will become 1 plus tan theta by 1 minus tan theta. That's your answer. Clear with this? Any doubts on this? Yeah, let's see the next one. Yeah, that's a decent main level question. Let's say we have a container. Inside you have a piston. This is filled with a liquid. Density rho 1, height h1. Rho 2, height h2. On top of it, you kept a block of mass m. And this space here has a pressure of 3p0. This is point A at the bottom. Right? The whole thing is a sealed container. Find the pressure at A. Straightforward question. I just mixed up few things. So you have a container which has a gas at a pressure of 3p0. You have a piston on top of it, you kept a block, and then you have two liquids, and the whole thing is getting compressed. What is the pressure at A?
So
Look
the
at this thing.
mass,
Let's start from the, yeah.
so the mass is included in that P naught, or it's like external.
How can you include that in P0?
I mean, the mass is making the pressure P naught, like something.
So meaning if you eat a lot of food and become fat, the atmosphere pressure changes.
No.
So why to बोल रहे हो तो? If I make that block heavier, for some reason the 3p0 changes.
No, I mean, in chemistry, the sir told us that it's for saying that pressure is constant, something like that.
No, ऐसा कुछ नहीं है. Let's start from the top. Let's ask you this thing. If I just draw the FBD of the piston, इसमें क्या क्या draw करोगे? You'll draw P0 into area and you'll draw mg, right? बस ना, piston पे force कितना था? 3p0 plus mg. So what is the pressure here? First thing, see, the gas का pressure is 3p0. Then the mg is acting on the piston. How much is that creating pressure? Mg by area. Then the red liquid is giving pressure rho 1g h1. Then the green liquid is giving pressure rho 2g h2. Where is all this going? At point A. Make sense? You can just keep adding one after another. Are you getting it? It's a scalar quantity. All sure with this? So the atmosphere, the gas will give 3p naught, the block will give mass by area, and the rho 1 and rho 2 will give rho 1 gh1 and rho 2 gh2. Easy question, but I just want to show there are three things there. That's it. Liquid ka pressure, block on a piston, and the atmosphere itself. Clear? Let's see one more. We have three containers. They all have same base area. It's not up to scale, but basically this area, and this area is same. This is point A, this is point B, this is point C. Case 1, this is there in HSE, 12th standard boards. They call this thing some hydrostatics paradox or something. Case 1, they're all filled to same height. Case 2, all have same volume of liquid. Maybe in all of them you pour 10 liters. Right? Arrange the pressures A, B, C in ascending or descending order. Is the question clear? We have three containers. Case 1, you filled them all to the same height of the liquid. What is the pressure? In case 2, you all filled them with the same amount of liquid, 10 liters. Then what is the arrange them in the pressure? Right. Get them both. I'll give you a minute out of analysis. Yeah, first was easy. All will have same pressure. Get the second one. Now, if you just look at this case 1 and case 2, it is easy to answer, but we'll discuss about that also. In case 1, same height. So then the pressure is simply P naught plus rho GH. Like I said, it doesn't depend on what is the shape of the container. Therefore, PA is equal to PB is equal to PC. What about case 2? Now in case 2, when you pour same amount of liquid, you can clearly see, let's say this A ka height is this much. B ka height will be definitely lesser because it is getting more broad on the top. And C ka height will be definitely more because it is getting more short on the top. So if you take this guy as a reference, you can clearly notice the heights will be different. So the highest pressure will be PC, then the next pressure will be PA, and the last guy will be PB. Got this? You can clearly see the heights will be different. Now my doubt is this. Since they all have same amount of liquid and the base area is same, shouldn't the pressure be mg by area? Then shouldn't the pressures be same? You're getting the problem there. Look at this. You said all have same amount of weight. Okay. So you are giving same amount of liquid. So technically speaking, this must be mg and this is area. So mg by area. This is mg, mg by area, mg, mg by area. So all should have same pressure. What is the problem? Why am I getting different pressures if the weight is same and the area is same? You getting my question? Hey, pressure depends on height, but how did you derive that? You derived it from forces only, na? So I'm going to the basic laws of motion. Since they have same amount of liquid, they all should have same weight. And since the base area is same, mg by area should have been the pressure, which is not the case. We are missing something. Right, Samyak? Right, Ovia. There additional. Nay, Srihari. So what is the catch? Don't look at the liquid. That is a mistake. Don't look at the whole container. Just draw FBD of the liquid. You will see something. If you draw FBD of the liquid, so the walls are pushing from the side. This is the force due to the walls. And this is your mg. Right? So pressure at A will be mg by area. When you take this guy, look at this, what happens? The walls are actually pushing it at an angle. So the walls are exerting an upward force and mg is downward. So pressure at B will be mg minus the walls ka force by area. So that was the catch. We should take the net force acting on the surface, right? It is not mg. Similarly, when you take this guy, FBD, here the walls are pushing down. F wall and mg and PC will be mg plus F wall by area. But if someone asks you what is the normal reaction on the ground, that will be same. Because then the wall ka force becomes internal. So pressure on the base is nothing but force on the base by area on the base. Are you getting it? The normal reaction on the floor is not the pressure on the base. So normal reaction on the floor will be same because all have same weight. I hope you're getting the difference. So pressure is not normal reaction by area. The pressure on the base is the force on the base by area. So the force on the base also includes the walls due to the force. Are you clear with this? So this is the explanation in terms of force. Yeah, in terms of height, you can always say, but how did you even get that height ka thing? You actually got it from here. Is this understood, everyone? So that is the reason, the argument, right? When you say the weight is same, area is same, so mg by area must be same, you're missing the point there. You have to include the force due to the walls. Let's see one more based on this. So let's say we have taken a container like this, whose radius is r, height is also r, the upper radius is 2r. And this whole thing is filled with a liquid. Rho outside of the pressure is P naught. Find the force due to the side walls on the liquid. Need to tell you, the whole thing will start looking like NLM. If you see, we're just drawing FBDs every time. Let's get this. What is the force on the liquid due to the side walls? Yeah, some good questions also mixed up with thermodynamics. So there's a lot of mixability there. When we do thermo, we will do problems based on fluid mechanics also there. So let's get this. Find the force due to the side walls on the liquid. Srihari, that's not the answer. How did you even get that so fast? And your dimensions are not matching. You just got rho g r is a pressure ka term. The forces, dimensions are not matching. Check it out. Find the force, Srihari, find the force. का thing rho 4/3 pi r cube g P naught का thing. P naught का thing is what, right? तू भी ना कुछ भी आंसर करते. P naught का thing it seems.
Sir, I
4
realized it
by
later,
3.
so I'm calculating.
सामने एक P naught का term भी एक आएगा, I guess. Let me ask you this. Can you guys just draw the FBD of the liquid? This is something I keep telling you. If you can't draw the FBD, your question is gone. Just draw the FBD of the liquid. I don't want the container. Because you're finding the force on the walls on the liquid, isn't it? The container or liquid, you can't take it as one system. Just draw FBD of the container, liquid, boss. You will see there. If you can't draw your FBD properly, you can't even start the question. Let's see whether you got it. So we are drawing FBD of the liquid. What are the forces? The atmosphere is pushing you from the top. That atmosphere is applying a force, right? P naught into 4 pi r square. The pressure at the bottom will be P naught plus rho g r. That is the pressure at the bottom. Into the area will be pi r square. Your own weight mg. And from here, the walls are also pushing you. And you can see symmetry is there. So the walls are actually pushing upward, F walls. And there, the green one is what I want you to find. So you can clearly see, I'll write it as FSW, F side walls must be equal to mg plus P naught into 4 pi r square minus P naught plus rho g r into pi r square. There. And how do you find m? You need to find m. So you can clearly see this. The whole thing is a frustum basically. It is like a cone. From there, someone removed this small cone and then you ended up with this shape. Isn't it? Where this cone ka radius was 2r, the height was also 2r. This cone ka radius was r and this height was r. So from that big cone, when you remove the small cone, you got left over with this 2r and r ka piece. I hope, is that making sense? It's just volumes. What is the volume of a solid cone? 1/3 pi r square h. That is 2r whole square. H is also 2r. This is 1/3 pi r square h. That is also r. So this thing turns out to be 7/3 pi r cube. That is the volume of that frustum there. So what is m? Density of the liquid, 7/3 pi r cube g. P naught 4 pi r square, P naught pi r square. So you'll be left out with P naught into 3 pi r square minus rho g pi r cube. 7 by 3 minus 1, that's 4 by 3. So rho into 4 by 3 pi r cube g plus P naught into 3 pi r square. That is the force due to the side walls. Check. Right, Samyak. Right, Arya. So P naught thingy nahi hai. The thing is 3 pi r square. Rho g r 5r plus 3. Oh yeah, there are dimensions match nahi hua. Check kiya? 5r plus 3. That is dimensionally wrong. How can you add r to a number there? All clear with this? Frankly speaking, other than saying pressure at the bottom is this and pressure is this, isn't the whole problem simple in NLM equilibrium? Clear with this? Next one. So we have a liquid here. The pressure is P naught. You immersed an half disk radius r into the liquid. From here to here, the depth is h. Right? And the density of the liquid is rho. So now when you keep the disk inside, right, the liquid is pushing the disk from both the sides. So total force is 0. I don't want the total force. I just want you to find the force due to the liquid on one face of the disk. Find force due to the liquid in the front face or the back face, any one face, due to the liquid on one face of the half disk. Right? Front face and back face, any one face. Are you clear what I'm asking? It's like if my phone is my disk and as you immerse it, the liquid is pushing from the front and liquid also pushing from the back. Net force is 0. I don't want that. I just want force due to one side. How much force is the liquid exerting on one face of the half disk? Or if that is confusing, I'll just write front face. Better. Let's get this. Now remember, as you go deeper and deeper, pressure is increasing, rho g x. So pressure is not constant. So you can't directly say pressure into area. You have to integrate, technically speaking. Try. Everyone should try. Anyone not convinced with not clear with the question, what I'm asking, please ask. So you took an half disk, you immersed it into the liquid at a depth h. Find the force on one half of the disk. Front face, right? Curved face, front face. Where is the confusion? It's a thin disk. There are only two faces, isn't it? Front and back. Front face. Disk, na, what you're thinking was this. If it is a hemisphere, na, what is it? Curved surface. Okay, what do you think is the answer then? Bhavya? If you don't need to integrate, then you can tell the answer in like one step, isn't it? Pressure into area. Na? What is the pressure? What is the pressure? यहाँ पे pressure कितना था? P naught plus rho g h. यहाँ पे pressure कितना था? P naught plus rho g h plus r. What is the pressure here? Something else. What is the pressure here? Something else. So how can we simply say pressure into area? At least अगर ये कुछ square plate होता था ना, I could have even argued and I would have taken the center. नहीं Srihari. What is that answer even actually? Your answer does not have h. Rho g h 0.5 r square. No, that is wrong. Listen. I know, bad integration, but you will see something interesting. I'll not even integrate the whole thing. Listen carefully, yeah? You get one really beautiful result. So how to integrate this? At a depth x or depth y, take a thin slice. Whose thickness is dy, right? And let's say this strip ka area is dA. So you normally should take dy and then you have to integrate the whole thing. Let the area of the strip be dA. Okay? So the force acting on this small strip is the pressure, which is P naught plus rho g y into dA. So if you want to find the force on that entire half disk, we have to integrate P naught into dA plus rho g into y dA. So if you can integrate this, my job is done. Okay? Now let's see something interesting. When you got this integral y dA, right? Multiply and divide this with sigma. What is sigma? Sigma is your mass per unit area. This will become 1 by sigma, which is constant. Sigma into dA becomes mass integral y dm. Now if you multiply this, and now you know y center of mass is integral y dm by integral dm. That would be total mass into y center of mass is integral y dm. And what is your total mass? Total mass is nothing but sigma into area. Or you can simply write this thing as y center of mass will be integral y dm by total mass. I think I can just leave it like that. You get your center of mass actually. So now when I integrate this, see what will happen. This will become P naught into area plus rho g. What is integral y dm? That is my center of mass. But what is integral y dm here? You needed a sigma there. Integral y dm. I'll just take out a sigma there. Wait. Y sigma dA is m by com. So integral y dA, mass is sigma into area. That will be area into y center of mass. So this becomes rho g integral y dA is area into y center of mass. So we got force on the half disk is P naught plus rho g y center of mass into area. Can you see the result? That means you can assume that entire thing, right? You can take the pressure at the center of mass. and multiply with the area, you're done. And we just proved this. If you observe, right, forget about the disk. Actually, if you see this proof, I proved it for any random area, isn't it? I didn't prove it for this disk. Where did I take it as a disk anywhere? I said area of the strip is dA. So this result, right, you can actually use it. So let's say if you have a liquid and if you have some amoeba shape inside, and as long as you know where is the center of mass, so the force on the one face is simply pressure at center of mass into the area. Now in our previous question, where is the center of mass of half disk? So this is the thing. So if you don't know your center of mass results, you're gone. Didn't I tell you your center of mass will keep popping up? When was the last time it came? It came in moment of inertia, parallax's theorem. Now it is coming in fluid mechanics. So the force for the half disk in the previous question, P naught plus rho g. Where is your center of mass? Center of mass is at 4r by 3 pi. Rho g, the height will be h plus 4r by 3 pi. This into area will be pi r square by 2 half disk. If you know this thing, you'll get the answer in like what, 10-15 seconds if you know your center of mass. Or else you have to integrate the whole stuff. Clear with this? So there's a trend, there is a thing, something you can keep seeing this. This works whenever the pressure is constant or pressure is a linear function, rho g x power 1. Did you observe? Potential energy of a system is potential energy of center of mass. That is mg h power 1. Momentum of the system is momentum of center of mass, mv power 1. Pressure rho g x power 1. Kinetic energy half mv square, it didn't work out. So whenever the functions are linear, and if it comes in the form of integral y dx thing, the center of mass always works. So this thing, there's only one condition. This is valid for constant pressures or linear functions. And when pressure changes linearly. For some reason, if the pressure does not change as rho g x, but rho g x square, this is gone. You have to integrate. Clear with this? And remember, this is for flat surfaces. Now you can actually extend this. You can do it even better. See, suppose if you have a piece like this, are you able to visualize how is this piece? Imagine this thing, okay? Your sister ka birthday cake is there and you put your hand and take a cake piece with your hand. You pull it out. Ever did that? So how will that piece be? Now, can you imagine that piece? It kind of looks like that. You put your hand inside the cake and just pull it out with your hand. You don't cut it properly. You get some random piece. Now, if someone asks you what is the force on that curved surface, now you can clearly see the pressure is acting on this whole thing horizontally. Right? And so we have a concept called projected area. We will talk about this. So basically, this is the projection. So the horizontal force on that curved surface. Simple logic. Since this thing is not moving left and right, it is in horizontal equilibrium. The horizontal forces must be same. So the horizontal force on that curved surface must be the pressure at center of mass of the projected area. So take the projected area, take its center of mass, take the pressure there. Into area of the projected area. Let me show an example that will make things more clear. Let's say you have a cylinder. And let's say this whole thing is immersed in a liquid. Now, if you look at the liquid actually, let's say this depth is h and this radius is r. Now, if you look at the liquid here, this whole liquid is pushing this curved surface. Like this, the pressure is non-uniform. We don't know how the pressure is acting. The whole thing is messed up, right? Now, this entire force, there'll be two components. So here, if you look at this area here, this blue one, that's your projected area. And this would be the center of mass of the projection. So this horizontal force on the curved surface right, will be pressure at the center of mass into area. So all those red forces ka horizontal thing. So what is the pressure there? P naught plus rho g r plus h into the area of the disk, which is pi r square. Is that making sense? So meaning when I take that cone, you can resolve the forces into two parts. There is this fx and there is one fy. It will be at an angle. So this will give you the fx part. Are you clear with this? It does not matter what shape it is. Matlab, if we can take a projection, see for this cone, when you take the projection, that will be the disk, isn't it? All getting with this? We will talk more about the projected area, but is this clear, everyone? So not only for a sheet, you can even do it for 3D shapes by taking a projection. So let's do one question on this, and then I'll show you more examples on this projected area. Projected area is a very important concept. It comes in 6 chapters. The first time you'll be seeing in fluid mechanics, then you will see it in surface tension, then you will see it in electrostatics, magnetism, modern physics. It does keep popping up at multiple places, so quite a useful concept. Ishman, clear with that projected area? Where are you? Yeah. So let's say we have a pool. In that you kept a cylinder, long cylinder. And this thing separates two different liquids. So what you did, you started pouring liquids on both the sides. On one side, you poured a liquid exactly till this height. The density is 2 rho and the height of the liquid is r. The other side, you poured a little more denser liquid, 3 rho, and the height of the liquid is h. Find h if the cylinder is in equilibrium. Obviously, you can't pour the same height. If you pour the same height, the left side, the pressure will be more because the density is 3 rho. Find the height of this green liquid if the system is in equilibrium. Let's see how will you do this. Hope the question was clear. Now, this concept I want you to use. basically the 3 row ka force on this part and the 2 row ka force on this part, they must be equal horizontally. That's the reason the cylinder is not moving left and right. More about projection, we will talk in more detail in the next class. But for now, just take it this much. The simple logic is this. Suppose if you take a random slice like this, the horizontal forces will act like this, right? So the horizontal forces must be equal to the force on this straight part. It comes from equilibrium, or kuch nahi. It is just because the system is at rest. Right. I'll give you a minute or two. Near Samyak. You missed something there. See. One thing is clear, the force due to the 3 row and the 2 row in the horizontal direction is equal. Horizontal direction, not the net force. There is a vertical component also. So the green one is acting on this part. The red one is acting on this part. So when you take this green one this thing, this projection, I'm bad at drawing this. Doesn't it look something like this? So the projection of this will be this rectangle, isn't it? Do you agree? What is the height of that rectangle? H. What is the length of the rectangle? L. Do you guys agree with that rectangle there? Now, you tell me, what is the force acting on the rectangle? Pressure at the center of mass. So that is this point here, center of mass, which is at h/2. That means the force due to the 3 row liquid will be the pressure at the center of mass, which is 3 row G. Height of the center of mass is h/2. That is the pressure at the center of mass. We are ignoring P0 because it will cancel on every direction because the whole thing is exposed to atmosphere. P0 will cancel on both the sides. Because the whole body is exposed, so P0 term will cancel anyway. Into that area of that rectangle, which is L into H. That's a projected area. So basically the horizontal force on this curve must be equal to the horizontal force on the rectangle. And where is the center of mass? h/2. So this will be 3 rho G h/2 LH. Is that making sense? Right, Obya, you got it. And what about this thing? So when you make a rectangle for this will be R, this will be L, this will be the center of mass, and this will be height r/2. So the force due to the 2 row liquid, same story, density is 2 row, G, height of the center of mass is r/2 into the projected area, which is L into R. So force due to 3 row must be equal to force due to 2 row. 3 rho G h square L/2 must be rho G R square L. Rho G will cancel, L will cancel. We end up with H is equal to root over 2/3R. Is that making sense, everyone? Right, Amit. So pressure mein you will get one H by ka term, and when you take the area, you'll get one more H by ka term. Is this making sense, everyone? How to do? Are you getting the horizontal projection ka meaning? You're getting the logic, right? Doesn't matter. Like the thing is this: no matter what kind of weird shape you take, this is my argument. Whatever is this force acting on this, it will have two components, an Fx and an Fy. Forget about Fx. the force acting on this rectangle must be also equal to Fx. Make sense? And just now we proved when you take a flat surface, the force on a flat surface is pressure at the center of mass into area. Are you clear, everyone? How we just made this into for 3D things. Okay, so that's a bit about the pressure stuff. So next class when we catch up, we'll continue from here. We will do more. Next class we will finish with the pressure part, and also we will start off something called buoyant force and all that stuff. I'm sure you studied that in school, but yeah, we will do much better ones. Okay, with that we'll wrap up for that day. And do remember there's a test online, so make sure to give. And do finish your rotation ka solving. Like the notes itself is pretty big, so make sure to do it again. So yeah, any doubts, anything else, please stay back and ask. Also free to leave. I'll see you guys again on Thursday.